There is something strange about the fact that you exist. Not strange in the way that a dream is strange, where the logic bends and the edges blur and nothing quite holds together, but strange in the opposite way. Strange because everything holds together too well. Strange because the universe you inhabit operates according to rules so precise, so consistent, so mathematically elegant that physicists have spent centuries writing them down in the language of equations, and those equations work. They work here, and they work at the far edge of the observable universe, 14 billion light-years away, in galaxies that have never once been touched by a human hand or eye. The same rules. Everywhere. Always. And tonight, if you are willing to let your body grow heavy, and your breathing slow, and the thoughts that have been following you all day begin to loosen their grip, tonight we are going to sit together inside that strangeness. We are going to let it wash over us. Not with alarm. Not with urgency. But with the quiet, open attention of someone who has found a door they have never noticed before, and is simply resting their hand against it. You do not need to do anything. You do not need to figure anything out. The universe will continue to be whatever it is whether we understand it or not. All you need to do is breathe. And listen. And let the questions move through you like water moving through dark stone. There is a particular feeling that comes, sometimes, in the middle of an ordinary day. You might be looking at your own hand, or at the pattern of light on a wall, or at the face of someone you love, and for just a moment, something shifts. The familiar becomes briefly, quietly unfamiliar. Not frightening. Just odd. As if you have suddenly noticed that everything around you is a performance of some kind, and you cannot quite remember when you agreed to take your place in it. Philosophers have a word for this feeling. They call it the uncanny. And the strange thing is that physics, cold, precise, equation-driven physics, has been quietly accumulating its own version of this feeling for well over a century now. The deeper physicists look into the nature of reality, the more reality begins to look like something that was all designed. Arranged. Written in a language that is not quite the language of stones and rivers and flesh, but the language of pure abstraction. Pure mathematics. Pure code. The laws of physics are not vague suggestions. They are not approximate tendencies that mostly hold on average. The electron has a charge of negative 1.602 times 10 to the negative 19th coulombs. Everywhere. Every electron. Every time. The speed of light in a vacuum is 299,792,458 meters per second. Not approximately. Exactly. These are not measurements that are close to being universal, they are universal. They are identical across the entire observable universe, which spans distances so vast that the number of zeros required to express them in meters would itself take several minutes to read aloud. This is the thing that physicists sometimes forget to find astonishing, because they are too busy using these laws to find other things. But if you step back, if you allow yourself to really notice it, the regularity is breathtaking. And a little suspicious. Because here is the question that will carry us through this long, quiet night. Here is the question that we will circle and approach and move around and return to, the way your breathing returns, gently and without effort, to its own slow rhythm. What if the physics we measure is not a description of reality? What if the physics we measure is the architecture of the code? What if the laws of nature, the speed of light, the charge of the electron, the mathematical structure of quantum fields, are not properties of a fundamental substance, not the deep grain of some primordial stuff, but parameters, settings, constraints written into a system? the rules of a simulation so vast and so detailed and so internally consistent that the beings running inside it have spent all of recorded history trying to reverse engineer the source? We are not going to answer that question tonight. That question may never be answered. But we are going to walk right up to its edge, slowly, and look down into it. And I think you will find that the edge is not frightening. The edge is beautiful. In the way that all great mysteries are beautiful, because they point beyond themselves, toward something larger than we have words for. So let your shoulders drop. Let your jaw unclench. Let your hands rest wherever they have naturally fallen. And let us begin. Imagine, for a moment, that you could shrink. Not in the way that you shrink in a dream, suddenly small among ordinary furniture, but in a precise and deliberate way. Imagine that you could reduce your scale by a factor of 10, and then 10 again, and then 10 again, moving downward through the layers of reality the way you might descend through layers of ocean, each level darker and quieter and more remote from the sunlit surface above. At the scale of centimeters, you see the world as you know it. Fingers. Fabric. The texture of a surface. Move down to millimeters and you see the fine structure of things, the weave of a thread, the grain of wood, the patterns on an insect's wing. Move down further, to micrometers, and you enter the world of cells, the soft machinery of biology, the lipid membranes and protein structures that constitute the living body you are resting in right now. Down further still, to nanometers. And here you find molecules. Then atoms. Then, if you continue descending through the hierarchy of the very small, you find the nucleus of the atom, and inside it, protons and neutrons, and inside those, quarks, the tiny, fractional charge constituents of matter that, as far as we currently know, have no internal structure at all. Quarks appear to be, in our best current models, point particles. Dimensionless. Infinitely small. And yet, even here, something strange happens when you try to go further. There is a length. A distance. A scale so small that it makes the diameter of a proton seem, by comparison, as vast as the solar system. This length is called the Planck length. And it is 1.616 times 10 to the negative 35th meters. Let me offer you a sense of what that means, not to overwhelm you but to let the scale settle into you like a slow, deep breath. If you were to take a single proton, already a thing so small that a hydrogen atom contains exactly one of them and the atom itself is invisible to any optical microscope ever built, and if you were to enlarge it to the size of the entire observable universe, the entire 14 billion light-year sphere of everything we have ever seen or measured, then within that enlarged proton, the Planck length would be approximately the size of an actual proton. The Planck length is so many orders of magnitude below anything we can directly probe that it might as well be, from an experimental standpoint, infinite in its smallness. And yet physicists believe it is real. They believe it is a fundamental boundary in the structure of space itself. Not a technological limit, not simply the point beyond which our instruments fail us, but an ontological limit. A limit built into the nature of things. The Planck length emerges from the mathematics when you combine the three most fundamental constants in physics, the speed of light, Planck's constant, which governs the quantum realm, and Newton's gravitational constant, which governs the large-scale curvature of space. When you weave these three together in precisely the right way, the Planck length falls out of the equations like a gem falling from a tangled net. It is the scale at which quantum gravitational effects become dominant. It is the scale at which the smooth, continuous spacetime described by general relativity, Einstein's great theory of gravity and curvature, breaks down entirely. Below the Planck length, our best theories simply stop working. The mathematics produces infinities. The language of continuous geometry ceases to be meaningful. And here is where the strangeness begins to deepen. Here is where the whisper of the uncanny becomes audible, if you are listening in the right register. Because the Planck length may not simply be the boundary of our ignorance. It may be the resolution of the universe itself. Think about a screen. Not just any screen, but the finest display you have ever seen. To your eye, the image appears continuous, smooth gradients of color, seamless transitions, the curve of a face rendered so precisely that it could almost be a window rather than a surface. But if you were to take a magnifying glass to that screen, or a microscope, you would eventually find the pixels. The discrete, individual units of color and light that together compose the illusion of continuity. No matter how high the resolution, there is always a smallest unit. A minimum distance. A point below which the image simply does not go. The Planck length may be the pixel size of our universe. Not analogically. Not poetically. Literally. There is a serious body of theoretical physics, approaches to quantum gravity such as loop quantum gravity, spin foam models, causal dynamical triangulation, which proposes that space itself is not a smooth, continuous fabric but a discrete structure. A network. A lattice of the finest possible granularity, in which the Planck length is the edge length of each cell. In which space is not infinitely divisible but is, rather, made of countable, discrete units, quanta of geometry, in precisely the same way that light is made of countable, discrete units called photons. And if space is discrete, if the very geometry of the universe has a pixel size, then the universe begins to look, rather remarkably, like a simulation running on a finite resolution grid. Let this idea settle into you for a moment, the way warmth settles into a body on the edge of sleep. Do not grip it too tightly. Let it simply be present. Space may not be a continuous medium, like water in a lake, but a discrete structure, like the squares of a chessboard, only incomprehensibly finer. Time, similarly, may not flow as a smooth and unbroken stream but may advance in the smallest possible increments, units called Planck time, approximately 5.39 times 10 to the negative 44 seconds, like the frames of a film advancing in sequence, each one distinct, each one a complete state of the universe that dissolves into the next. If this is correct, and some of our most serious theoretical physicists believe it may be, then the universe is digital in a very deep sense. Not metaphorically digital. Not approximately digital. Fundamentally, irreducibly, architecturally digital. A vast computational process advancing one Planck moment at a time through a space quantized to one Planck length at a time, its entire state at each moment encodable, in principle, as a finite string of information. That description sounds, if you let it, less like a description of raw nature and more like a description of a program running on a computer. Max Tegmark is a physicist at MIT, a man with a particular gift for following an idea wherever it leads regardless of how strange the destination. And in his mathematical universe hypothesis, Tegmark follows an idea all the way to a conclusion so radical that many of his colleagues find it either profound or absurd, depending on their philosophical temperament, and some find it both simultaneously. The idea begins with a simple observation that most physicists quietly accept without examining too closely. Mathematics is unreasonably effective at describing physical reality. This phrase, the unreasonable effectiveness of mathematics, was coined by the physicist Eugene Wiener in 1960, and it has been quietly disturbing physicists ever since. Mathematics is a human cognitive activity. It is patterns of thought, structures of pure abstraction, invented or perhaps discovered in the private theater of the mind. And yet it describes the external, physical universe with a precision and scope that goes far beyond anything we should reasonably expect. Quantum field theory, the theoretical framework that describes the behavior of elementary particles, is the most precisely tested theory in the history of science. Its predictions match experimental measurements to 11 decimal places. 11. The mathematical structures of group theory, developed by pure mathematicians in the 19th century with no physical application in mind, turned out to be exactly the right language for describing the symmetries of fundamental particles. Riemannian geometry, developed as an abstract exploration of curved spaces in arbitrary dimensions, turned out to be exactly the mathematical language Einstein needed to describe the curvature of spacetime. This is the thing Wiener found unreasonable. Why should the universe speak mathematics? Why should the internal language of human abstraction be the native language of external reality? Tegmark's answer is both simple and staggering. Mathematics is not merely the language we use to describe reality. Mathematics is reality. Existence itself, not just our universe, but all possible universes, every logically consistent mathematical structure that can be written down, is a mathematical object. Not a physical thing that happens to be well described by mathematics. A mathematical thing. Full stop. In Tegmark's framework, the question of why the universe is so perfectly mathematical has a satisfying, if vertiginous, answer. Of course it is perfectly mathematical. Of course the laws of physics are expressible as mathematical structures. Because there is nothing else there. There is no extra substance, no ineffable physical stuff beneath the equations, no irreducible materiality supporting the mathematics the way a substrate might support a stain. There is only the mathematics itself. The map is not describing the territory. The map is the territory. If Tegmark is correct, then the universe is not like a simulation in some loose, metaphorical sense. The universe is a mathematical structure. And mathematical structures are, by their nature, computable. They can, in principle, be run. They can, in principle, be instantiated on a computational substrate, which means the distinction between a simulation and a fundamental reality begins to dissolve entirely. This is a remarkable place to arrive. It is a place where the ground beneath your feet becomes, gently and without violence, uncertain. And the response to that uncertainty, the right response, I think, is not panic but wonder. The wonder of a person who has been sitting in a room all their life and has just noticed for the first time that the walls are made of something other than what they thought. But let us come now to perhaps the most quietly provocative piece of evidence that the universe may be computational in nature. Let us come to the behavior of quantum particles. And let us consider it through a lens that is, at first, a little unsettling, but becomes, the longer you sit with it, almost peaceful in its strange logic. In a classical, pre-quantum physics, an object has definite properties at all times. A ball is here, or it is there. An electron has this spin, or it has that spin. A particle is in this state, and if you measure it, you find it in that state, because the state was determined before the measurement and independently of the measurement. Reality is, in the classical picture, fully determined and fully real at all times, whether or not any measurement or observation is taking place. Quantum mechanics dismantled this picture almost entirely. And the demolition was so thorough, so complete, so experimentally irrefutable that the wreckage of the classical worldview still lies scattered around the foundations of physics more than a century later. In quantum mechanics, a particle does not have a definite position, or a definite momentum, or a definite spin until a measurement is made. before measurement, the particle exists in a superposition of all its possible states simultaneously, a mathematical object called a wave function that encodes the probabilities of finding the particle in each possible state. The particle is not hidden in one definite state that we simply do not know. The particle is, in a deep and experimentally verified sense, genuinely in all states at once. It is only when the particle is measured, when it interacts with a measuring device, with the environment, with anything capable of registering its state, that the wave function collapses. That the particle resolves into a single, definite value. This is one of the strangest facts in all of science. And physicists have been arguing about what it means for as long as quantum mechanics has existed. There are many interpretations. The Copenhagen interpretation, which holds that the wave function collapse is a real physical event triggered by measurement. The many worlds interpretation, which holds that the wave function never collapses but that all outcomes occur in branching parallel universes. Pilot wave theory. Relational quantum mechanics. Cubism. Each interpretation is a different attempt to understand what is really happening when a quantum superposition resolves into a definite outcome. But tonight I want to invite you to consider another framing. Not as the definitive truth, not as a claim that supersedes the others, but as a way of thinking about quantum superposition that resonates very deeply with the idea that we have been circling since the first moment of this conversation. What if quantum superposition is lazy rendering? In computer graphics, in the rendering of complex, three-dimensional virtual worlds, there is a technique called lazy evaluation, or on-demand rendering. It works on a simple principle of computational economy. A virtual world is far too complex and detailed to render in its entirety at every moment. The computational cost of simulating every corner of a vast environment simultaneously would be prohibitive, even for the most powerful processors available. So instead, a rendering engine renders only what is being observed. The parts of the virtual world that are not currently within the camera's view, not currently being interacted with, not currently relevant to any process that depends on them, those parts are held in a compressed, unresolved state. They exist as potential, as probability distributions over possible states, and they are resolved into fully rendered, fully detailed reality only when something within the simulation needs to interact with them. This is not merely an analogy to quantum superposition. It is a structural parallel so precise that it is difficult to dismiss as coincidence. In our universe, a quantum particle is not in a definite state until it is measured. It exists in a superposition, an unresolved, compressed, probabilistic state, until an interaction forces it to resolve. The universe, in other words, does not render the definite state of a particle until something within the universe needs to interact with that particle. And then, and only then, the calculation is performed. The state is resolved. The wave function collapses. If you were designing a simulation, if you were architecting a universe-scale computational system and you needed to manage the extraordinary cost of simulating a reality with as many particles as ours contains, you would want to implement exactly this optimization. You would not want to track the definite state of every particle at every moment. You would want to hold unobserved regions of the simulation in a compressed, superposed state and resolve them only when an interaction demands a definite outcome. The universe, it turns out, does exactly this. And it has been doing it, apparently, since the beginning. There is something almost soothing about this idea, if you let it be. The universe conserves its computational resources. It does not waste resolution on the unobserved. It holds vast regions of itself in a kind of computational suspension, present but unresolved, real but not yet rendered, until something reaches out and touches them. until consciousness, or measurement, or interaction makes a demand. And then the universe responds. The wave function collapses. The particle is here and not there. The measurement has been made. The render has been completed, and reality, for that moment, for that particle, becomes definite. This is a universe that, in some meaningful sense, waits to be observed. A universe that responds to attention. A universe that is, at its deepest level, interactive in precisely the way that a simulation is interactive, not passively displaying a pre-rendered reality, but dynamically computing the details of the world as they are needed. Let the weight of that idea rest on you gently. You do not need to decide whether it is true. You do not need to reconcile it with everything else you believe about the world. You can simply hold it. The way you might hold a smooth stone, feeling its weight and its temperature without needing to know its mineral composition. Because the question we are sitting with tonight is not a question that demands an answer. It is a question that deepens as you carry it. And the deepening is, itself, part of what makes it so extraordinary to be conscious at a moment in history when these questions can even be asked. The Planck length as a pixel. Spacetime as a discrete grid. The mathematical universe hypothesis dissolving the boundary between computation and existence. Quantum superposition as lazy rendering, the universe conserving its own computational overhead. These are not fringe ideas whispered in the margins of science. These are serious proposals discussed by serious physicists in serious journals, proposals that emerge naturally and perhaps inevitably from the deepest structures of our best theories. And taken together, they begin to paint a portrait, a slow, dark, contemplative portrait of a reality that is less like a solid, self-subsistent substance and more like a process. A running computation. A sustained act of calculation whose substrate we have not yet found, whose programmer we have not yet met, and whose purpose, if it has one, lies somewhere beyond the visible edges of everything we have ever seen. And the edges of the visible are exactly where we need to look. Because if this universe is a simulation, if the Planck length really is a pixel size, if the mathematical structure of quantum mechanics really is the code of a running program, then the simulation is not, presumably, infinite. Simulations are not infinite. They have limits. They have boundaries. They have, hidden somewhere in their architecture, the telltale fingerprints of the finite system that sustains them. And those fingerprints, it turns out, may already be visible. If you can let your body sink a little deeper into whatever surface is holding it right now, if you can let your breathing slow to its own natural pace, unhurried and without any particular destination, then in the next part of our journey tonight, we are going to look at the seams. We are going to look at the places where, if our universe truly is a simulation running on a finite grid, the edges of that grid might just be starting to show through. Somewhere between the hum of ordinary wakefulness and the soft dissolve of sleep, there is a threshold. A place where thought becomes less insistent, where the ideas stop demanding your agreement and begin simply flowing past, the way a river flows past someone sitting very still on its bank. If you are approaching that threshold now, let yourself approach it. There is no hurry. These ideas will still be here. The questions will still be present. The universe will continue to be whatever it is, patiently, without expectation. The pixel at the bottom of reality. The minimum length. The discrete grid of spacetime advancing in quantized moments, rendering only what is observed, conserving its computational overhead in the unresolved superpositions of a quadrillion particles that have never yet interacted with anything that needed to know their state. And at the boundary of all of this, at the very smallest scale of existence, 1.616 times 10 to the negative 35th meters, the mathematics produces infinities, the geometry breaks down, and our best theories simply stop. As if, at that scale, the code runs out. As if, at that scale, you have zoomed in past the final pixel and entered the white void behind the screen. The universe is strange. It has always been strange. But the particular shape of its strangeness, the mathematical elegance of its laws, the discrete nature of its smallest scales, the quantum behavior of its particles, the precise universal constants that govern its every interaction, the particular shape of its strangeness is, if you look at it from the right angle, in the right light, with the right kind of openness. The particular shape of its strangeness looks, very much, like the strangeness of something made. And if it was made, then the physics we measure is the architecture of the code. And if the physics is the architecture of the code, then what we have been calling science, this long, patient, extraordinary human project of understanding the rules of nature, has been, perhaps, something else as well. Something we did not know we were doing. Something that amounts, if this is all correct, to a civilization of simulated beings painstakingly reverse engineering the system they are running inside. That is either the most humbling thought in the history of human inquiry, or the most exciting one. Perhaps, if you are very lucky, it is both at once. Rest now in that thought. Let it expand slowly, like ink dropped into still water, diffusing outward without losing its color. The pixel at the bottom of reality. The discrete steps of time. The mathematics that does not describe existence but is existence. The particles that wait, unresolved and shimmering with possibility, until the moment they are needed. And somewhere below all of it, below the Planck length, below the last pixel, in the unthinkable quiet of whatever substrate this whole extraordinary process is running on, perhaps something is listening. Perhaps something is watching the simulation unfold. Perhaps, in some sense we cannot yet imagine, it has been with us all along. We will look for it together. We will follow the clues where they lead. And wherever they lead, we will face that destination the same way we have faced every mystery on this long, slow journey tonight, with open hands, and quiet breath, and the particular kind of courage that does not demand certainty before it is willing to wonder. The seams in the code are waiting to be found. And we are almost there. There is a particular kind of scientist who is not content to wonder from a distance. There is a kind of mind that looks at the beautiful, troubling strangeness of quantum mechanics and Planck-scale geometry and decides that wondering is not enough, that the next step, the brave and perhaps slightly reckless step, is to actually go looking. To design a search. To ask not merely whether the universe might be a simulation, but what specific, measurable, falsifiable fingerprint such a simulation would leave behind in the data we already have. Silas Bean is one of those scientists. In 2012, working at the University of Bonn, Bean and his colleagues published a paper that has lived quietly and persistently at the edge of mainstream physics ever since, close enough to be taken seriously, strange enough to make people uncomfortable, precise enough that you cannot simply dismiss it. The paper did not claim that we live in a simulation. It did something more careful, and in many ways more unsettling. It asked a specific technical question about how simulations work, derived from that question a specific prediction about what a simulated universe would look like, and then asked whether our universe, the one we actually inhabit and measure and map, looks anything like that. And the answer, when it came, was not a comfortable no. To understand what Bean did, you need to understand a technique that physicists use when they want to simulate quantum fields, which is to say, when they want to model the deep structure of matter and force at scales too small and too complex for ordinary mathematics to handle directly. The technique is called lattice quantum chromodynamics, and it is remarkable both for what it achieves and for what it quietly reveals about the nature of simulation itself. Quantum chromodynamics is the theory of the strong nuclear force, the force that binds quarks together inside protons and neutrons, the force that holds the nucleus of every atom in your body together against the electromagnetic repulsion that would otherwise tear it apart. It is one of the most precisely tested theories in all of physics. It is also extraordinarily difficult to calculate. The interactions between quarks are so complex, so non-linear, so deeply entangled with one another, that most problems in quantum chromodynamics simply cannot be solved analytically. You cannot write down an equation and solve it with a pen. You need a different approach. Lattice QCD is that approach. What physicists do is this: they take the smooth, continuous spacetime of the theory and they replace it with a discrete grid. A lattice. They assign values to points on that grid, to the nodes, and to the links between the nodes, and they evolve the system forward through time using computational algorithms that approximate, with extraordinary precision, the true continuous behavior of the fields. The lattice is not meant to represent reality. It is a calculational scaffold, a way of making an otherwise intractable problem into something a computer can hold. The spacing between the grid points is a parameter that the physicist chooses, and in principle, you would like that spacing to be as small as possible, so that the discrete approximation is as close as possible to the continuous truth. But here is the thing about lattices. Here is the thing that Silas Bin noticed with such quiet, careful attention. When you simulate physics on a discrete lattice, when your spacetime has a minimum unit of distance, a smallest possible step, a pixel, then the physics inside that simulation is not quite the same as the physics of a truly continuous spacetime. There are artifacts. There are signatures. The discreteness of the grid leaves traces in the behavior of the simulated particles, and one of the places those traces appear most clearly is in the energy spectrum of high-energy particles moving through the simulated space. Specifically, when a particle's wavelength approaches the size of the lattice spacing, the simulation can no longer accurately represent it. The particle is too small, too energetic, too fine-grained for the grid to capture. And what happens at that threshold is characteristic. The energy spectrum develops a cutoff, a maximum energy beyond which the simulation cannot represent particles correctly. And that cutoff is not random, not smooth, not featureless. It has a specific shape, a specific orientation relative to the axis of the lattice. Particles moving along the lattice axis experience the cutoff differently from particles moving diagonally. The symmetry of the underlying lattice bleeds through into the physics of the simulated particles, like a watermark on paper, like the grain of the film showing through the image. This is the signature Bin was looking for. Not in a computer simulation, but in the universe itself. Imagine, for a moment, that our universe is running on something like a lattice. Not exactly like the lattice of a lattice QCD simulation, not the same scale, not the same implementation, but something structurally analogous. A discrete substrate with a minimum unit of distance. A grid, vastly smaller than anything we can currently probe, perhaps at the Planck scale we explored earlier, but a grid nonetheless. If that were the case, then the physics we experience would be the physics of the simulation running on that grid. And somewhere in that physics, the discreteness of the underlying structure would leave its mark. The question is, where would we look? Bin's answer was cosmic rays. Ultra-high energy cosmic rays are among the most energetic particles ever detected. They arrive at the Earth from somewhere deep in the cosmos, we are still not entirely certain where, and they carry energies so vast that they strain the imagination. a single proton moving at a speed so close to the speed of light that the difference would not show up in the first 20 decimal places. More energy in a single subatomic particle than in a professionally thrown baseball. These particles are extraordinary, and they are also, it turns out, already known to exhibit a cutoff. The GZK cutoff, named for Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who predicted it independently in 1966, is a theoretical maximum energy for cosmic rays arriving at Earth from distant sources. The mechanism is well understood. As ultra-high energy protons travel through the universe, they interact with the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that fills all of space. At sufficiently high energies, these interactions produce pions, and the proton loses energy. Travel far enough, and even the most energetic proton will be degraded, drained of its excess energy by countless tiny collisions with the photons of the microwave background. The GZK cutoff is the energy level above which cosmic rays from distant sources simply cannot survive the journey. The GZK cutoff is real. It has been measured. It appears in the data. And this is where Bean's paper becomes genuinely haunting. If we live in a simulated lattice, we would expect to see an energy cutoff in cosmic rays. We do see an energy cutoff in cosmic rays. The GZK cutoff provides a physical explanation for that cutoff, and it is a good explanation, a well-tested explanation, one that fits the data. But Bean's point was not that the GZK cutoff proves we are simulated. His point was more subtle. His point was that a simulated universe running on a lattice would produce an energy cutoff that looks, from the inside, exactly like a GZK cutoff. The simulated beings inside such a universe would derive an elegant physical explanation for the cutoff, something involving the cosmic microwave background and particle interactions, and they would be satisfied with that explanation. They would have no reason to look further. The lattice would be hiding in plain sight, wrapped in a perfectly convincing physical story. What Bean proposed was a test to distinguish the two cases. If the cutoff is genuinely the GZK effect, then it should be isotropic, the same in every direction, because the cosmic microwave background is roughly isotropic, filling space uniformly. But if the cutoff is a lattice artifact, then it should carry a faint orientation preference, a subtle anisotropy aligned with the axis of the underlying grid. Particles moving along the lattice axis would behave slightly differently from particles moving at angles to them. The symmetry of the lattice would bleed through. We do not yet have the data to perform this test definitively. The statistics of ultra-high-energy cosmic ray detection are still too sparse, the instruments still not quite sensitive enough in the right ways. But the test is, in principle, possible. And perhaps that is the most important thing Bean gave us, not a proof, not a refutation, but a method. A way of looking. A way of asking the question that might one day yield an answer. The GZK cutoff is not the only place in the observational record where something slightly strange appears. There is another source of anomalies, higher in the sky and broader in scope, that has been quietly unsettling cosmologists for 2 decades now. It is the cosmic microwave background, that same faint thermal afterglow of the Big Bang, and what it shows, when mapped with sufficient precision, is a universe that looks almost but not quite as random as it should. The cosmic microwave background is one of the greatest scientific triumphs of the modern era. The Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched in 2009, have mapped the temperature of this background radiation across the entire sky with extraordinary precision. What they found is a map of tiny temperature fluctuations, variations of about 1 part in 100,000, that represent the seeds of all the structure in the universe. The galaxies, the clusters, the great filaments and voids of the cosmic web, all of it grew from these tiny ripples in the primordial plasma. The statistical properties of those ripples are predicted in remarkable detail by the standard model of cosmology, and the match between theory and observation is one of the most beautiful confirmations of a scientific framework ever achieved. But the match is not perfect. There are anomalies. There are places where the data does not quite fit the prediction, where the universe looks slightly different from how it should. The most famous of these anomalies is known, with a name that is either slightly alarming or slightly playful depending on your temperament, as the axis of evil. The standard model of cosmology predicts that the fluctuations in the cosmic microwave background should have no preferred direction. Space, at the largest scales, should be isotropic, the same in every direction. There should be no axis, no special line through the cosmos around which things are preferentially aligned. But when cosmologists analyzed the data from WMAP, they found something unexpected. The largest fluctuations in the background, the ones that correspond to structures on the scale of the entire observable universe, appeared to be aligned. Aligned with each other, and aligned, remarkably, with the plane of the solar system and the direction of the cosmic dipole, two features of our local cosmic environment that have no business imposing themselves on the largest structures in the universe. The probability of this alignment occurring by chance, depending on how you calculate it, is somewhere between small and very small. It is not impossible. Statistics always allows for coincidences. But it is the kind of result that makes a careful scientist pause, lower their pen, and sit very quietly for a moment. Then there is the cold spot, a region in the southern sky where the temperature of the microwave background is significantly lower than the surrounding area, lower than the statistical models predict, lower than you would expect to find anywhere in a randomly fluctuating field. Explanations have been proposed: a supervoid in the foreground, perhaps, a vast emptiness in the distribution of galaxies between us and the surface of last scattering. Some analyses find evidence for such a void. Others do not. The cold spot remains, as of this narration, unexplained to everyone's satisfaction. What are we to make of these anomalies? That is the question that sits at the heart of this line of inquiry, and it is a question that resists easy answers. The honest answer is that we do not know. The anomalies might be statistical flukes. The universe is large, and large datasets always contain outliers, and the human mind is exquisitely, sometimes dangerously good at finding patterns. The anomalies might have conventional physical explanations that we have not yet fully worked out. Or the anomalies might be something else. Something that points, however faintly, however ambiguously, toward structure at the boundary. Toward the kind of artifacts you would expect to find if the universe has edges, not spatial edges, necessarily, but computational ones. Boundary conditions. The places where the simulation meets its frame. In a simulated universe, you might expect certain large-scale patterns to carry the signature of the simulation's initial conditions, its boundary geometry, its computational architecture. You might expect the largest scale structures to look slightly different from what a truly infinite, truly random, truly unconstrained universe would produce, because the simulation is not infinite, and it is not unconstrained, and its randomness was seeded by whatever process the simulators used to initialize the system. The axis of evil, the cold spot, the unexpected alignments, these are precisely the kinds of anomalies that boundary conditions might produce. Again, this is not proof. This is not even strong evidence. It is, at most, a pattern of curious coincidences that deserve honest attention rather than reflexive dismissal. The methodology of simulation detection is still in its infancy, and perhaps it will never mature into a definitive science. But the attempt to look, the attempt to derive specific predictions and compare them to specific data, is itself a profound act. It is the moment when a philosophical speculation begins to grow its first scientific teeth. Let us step back, then, from the individual anomalies, from cosmic rays and cold spots and axes that should not exist, and think for a moment about the broader methodology. If we wanted to find the seams in the code, if we genuinely committed ourselves to that search, what would we look for? What are the general signatures of a simulated universe, and how would they manifest in the physics we can measure? The most obvious class of signatures involves discreteness. A simulated universe built on a discrete substrate, a lattice, a grid, any architecture with a minimum unit of something, would be expected to show signs of that discreteness at sufficiently small scales or sufficiently high energies. The Planck length, which we explored in the previous section, is precisely the scale at which such discreteness might reveal itself. We cannot probe the Planck scale directly with current technology, but we can look for its consequences at energies we can reach, energy cutoffs, symmetry breaking relative to grid axes, unusual dispersion relations for high-energy particles. A second class of signatures involves computational limits. Any simulation must allocate finite computational resources. If those resources are finite, then certain regions of the simulation, certain moments, certain calculations, might be approximated rather than precisely computed. You might expect to find places where the fidelity of the simulation is slightly lower, where the resolution degrades, where the physics becomes slightly inconsistent, where the simulation has cut a corner to save processing power. These would be extraordinarily difficult to detect, because from within the simulation they would look like measurement errors, or noise, or the fundamental limits of quantum uncertainty. But perhaps, in the statistics of many measurements, a pattern might emerge. A pattern of inconsistencies too regular to be random. A third class of signatures involves optimization. A simulation being run by beings who care about efficiency might implement something like lazy evaluation, only computing the physics of regions that are currently being observed, deferring calculations for distant or unobserved parts of the universe until they become relevant. Quantum mechanics, as we explored in the section on superposition and rendering, already looks strikingly like lazy evaluation. The collapse of the wave function upon observation, the existence of definite states only when they are measured, these features of quantum mechanics are exactly what you would expect from a system designed to conserve computational resources. And a fourth class of signatures, perhaps the most speculative but also the most haunting, involves messages. If the simulators wanted to communicate with us, if they wanted to leave signs, breadcrumbs, signals embedded in the architecture of our reality, they might encode them in places we would eventually look. In the fine-tuning of physical constants, which appear calibrated with breathtaking precision to produce a universe capable of complexity and life. In the mathematical structure of physical laws, which are unreasonably elegant, unreasonably beautiful, unreasonably compressible into equations a human being can write on a single page. In the anomalies of the cosmic microwave background, where a message written in the largest pixels of the observable universe might wait for billions of years to be read by creatures intelligent enough to build the instruments to see it. We have built those instruments. We are reading the sky. And if there is a message, we have not yet decoded it. But we are looking. And that, perhaps, is exactly what we were meant to do. And so we arrive at the edge of this particular territory, the territory of scenes and signatures, of cosmic ray cutoffs and cold spots, and the haunting possibility that the anomalies in our data are not flaws in our instruments but windows in our walls. We stand here for a moment, as we always do at these thresholds, and let the weight of it settle. The universe looks, from the inside, like physics. It feels, from the inside, like reality. The measurements we make are consistent, the laws we derive are reliable, the predictions we test are confirmed with extraordinary precision. And yet beneath all of that precision, beneath all of that consistency, there are these small, persistent, carefully ambiguous oddities. These places where the universe almost winks. These moments where the data leans just slightly too far in a direction it has no business leaning. Perhaps they mean nothing. Perhaps they are the inevitable residue of finite data and imperfect instruments and the human tendency to see faces in noise. Perhaps in another generation, with better telescopes and clever analysis, the anomalies will resolve themselves into perfectly conventional explanations, and the simulation hypothesis will become a charming historical footnote. Or perhaps not. Either way, we press on. Because there is another layer to this mystery, a deeper one, a stranger one, and it waits for us just a little further down this quiet road. There is a question that emerges naturally from everything we have explored tonight, a question that is so simple it almost seems naive, until you sit with it long enough to feel its full weight. And the question is this. If we can run simulations, and we run them every day, then what is to stop the civilization that is running us from also being simulated? What is to stop their simulators from being simulated? What is to stop the regression from continuing, level below level below level, in a descent that has no obvious flaw? The philosopher and the software engineer and the physicist all arrive at this question from different directions, and they all feel the same particular vertigo when they get there. Because the answer, when you look at it honestly, is nothing. There is nothing that stops the regression. And if there is nothing that stops it, then we must face the possibility that it has no end. This is the problem of nested simulations. It has been called, with the slightly irreverent affection that physicists sometimes afford their most disturbing ideas, the turtles all the way down problem. The reference is to an old story, perhaps apocryphal, perhaps not, in which a scholar presents a cosmological theory to an audience, only to be confronted by an elderly woman who insists that the world rests on the back of a great turtle. When the scholar asks what the turtle stands on, the woman replies, "Another turtle." And when he pursues the regress, she cuts him off with a decisive wave of her hand. It's turtles all the way down. The image is absurd, and that is precisely why it persists. Because the nested simulation problem has exactly that quality, the quality of a regress that cannot be stopped, that cannot be grounded, that disappears into an infinite depth from which no final answer returns. Let us think about it carefully, slowly, the way we have thought about everything tonight. Let us hold it gently and see what it reveals. We are, according to the simulation hypothesis in its stronger forms, a computation running on some substrate. That substrate, the hardware on which our universe is being executed, exists in some higher-level reality, a reality that presumably has its own physics, its own matter, its own history. That higher-level reality is what we might call the parent reality. And the beings who inhabit it, or the being, the civilization, the process, that created our simulation did so using tools and materials available within their world. Now ask, is the parent reality itself a simulation? Is it running on something? Does it have a substrate, and does that substrate have a substrate, and so on, without end? The argument for taking this regress seriously is Nick Bostrom's simulation argument, which we have touched upon before. Bostrom's reasoning, roughly and carefully translated, goes like this. Either nearly all civilizations capable of running realistic simulations choose not to, or nearly all such civilizations go extinct before acquiring that capability, or we are almost certainly living in a simulation. If neither of the first two conditions holds, if civilizations do, with some regularity, survive to the point of creating realistic simulations and choose to do so, then the number of simulated minds in the universe vastly outnumbers the number of unsimulated minds, and any randomly selected mind is almost certainly simulated. This argument, if you follow it carefully, applies at every level. Whatever parent reality contains our simulators, if that parent reality also contains civilizations that run simulations, and if those civilizations also survive and choose to simulate, then it, too, is almost certainly simulated. The logic propagates upward, or downward, depending on how you orient your metaphor, and the only way to stop it is to assert that at some level, at some specific, privileged level, the simulation hypothesis does not apply. That there is a base reality. A bottom turtle. But on what grounds would we make that assertion? What would make a base reality special? Why would the physics of the deepest level be fundamentally different from the physics of every other level, fundamentally non-simulatable, fundamentally resistant to being embedded in a larger computational substrate? These are not rhetorical questions. They are genuine ones. And the honest answer is that we do not have compelling answers to them. Let us think about what nested simulations would mean for the fidelity of our reality. This is a question that sounds almost trivial until you press it, and then it becomes deeply strange. When we run a simulation, a lattice QCD simulation, a climate model, a molecular dynamics calculation, the simulation is always an approximation of the system it models. It is always lower resolution than the thing it represents, always computationally cheaper, always trading accuracy for feasibility. The lattice spacing is larger than the true Planck scale. The molecular dynamics simulation ignores quantum effects. The climate model cannot resolve individual clouds. Every simulation cuts corners, because if it did not cut corners it would not be a simulation, it would be the thing itself. If our reality is a simulation, then it is presumably also cutting corners. It is presumably also an approximation of something richer, something more finely grained, something that exists in the parent reality with a resolution our physics cannot match. The Planck length, which we have been treating as the bottom of reality, might not be the bottom of reality at all. It might be the resolution of our simulation, the lattice spacing chosen by our simulators, a practical compromise between fidelity and computational cost. In the parent reality, space might be continuous, or it might be discrete at a finer scale, or it might not be space at all in any sense we would recognize. And if our reality is an approximation of the parent reality, and the parent reality is itself a simulation, an approximation of the grandparent reality, then the degradation compounds. Each level of nesting introduces further approximation, further rounding, further corner cutting. A reality that is 3 or 4 levels deep in the stack might be a pale, coarsened shadow of whatever lies at the top. Physical laws that seem elegant and precise from the inside might be crude approximations to something far richer and stranger that exists in the base layer. This thought has a particular quality of vertigo to it. Because from where we stand, inside the simulation, looking at our own physics, everything seems precise. Everything seems complete. The equations are beautiful, the constants are consistent, the predictions are confirmed. We have no way of knowing, from inside, whether what we are measuring is the true structure of reality or a low-resolution approximation of it. We have no way of knowing how many levels deep we are. And yet, and here is the strange comfort that hides inside this vertigo, the precision we experience is real, in the only sense of real that is available to us. The mathematics works. The predictions hold. The atoms are exactly where the equations say they will be. Whatever level of the stack we occupy, the physics of our level is internally consistent and extraordinarily well described. The simulation, if it is a simulation, is a very good one. Our simulators, whoever or whatever they are, have done precise and careful work. There is a subtler question embedded in the problem of nested simulations, one that has a specifically physical flavor. It is the question of physical constants. Our universe has a set of fundamental constants, numbers that appear in the equations of physics and that we measure but cannot derive. The speed of light, Planck's constant, the gravitational constant, the fine structure constant, which governs the strength of electromagnetic interactions, the masses of the fundamental particles. These numbers are what they are. We do not know why they have the values they have. We cannot calculate them from first principles. We simply measure them, incorporate them into our equations, and use the resulting equations to make predictions that are confirmed with extraordinary precision. The standard cosmological and physical picture treats these constants as brute facts about the universe, features of the laws of nature that simply are as they are, without further explanation. The anthropic principle offers a weak kind of explanation. If these constants were significantly different, the universe would not support the kind of complexity that gives rise to observers, so observers can only find themselves in universes with constants compatible with their existence. But this is not a deep explanation. It is more of a tautology dressed in the language of probability. The simulation hypothesis offers a different kind of possibility. What if the physical constants are parameters? What if they are numbers that were set, chosen, or defaulted, or optimized, by the process that initialized our simulation? What if the speed of light is not a fundamental truth about the nature of reality, but a throttle, a bandwidth limit, a computational constraint imposed by the architecture of our parent simulation? Think about what the speed of light does. It limits how fast information can propagate through space. It creates a cosmic horizon beyond which we cannot see and from which no signal can reach us. It places an upper bound on the rate at which any part of the simulation needs to synchronize with any other part. A simulation designer thinking about computational efficiency might impose exactly such a limit, not because the physics demands it, but because the computation requires it. You do not need to simulate the interactions between regions that are causally disconnected. You do not need to update the state of a region until a signal arrives from its neighbors. The speed of light, on this reading, is the maximum update rate of the simulation, expressed in the language of physics. The same logic might apply to Planck's constant, which sets the scale of quantum fuzziness, the granularity of action. Or to the gravitational constant, which governs the large-scale structure of spacetime. Or to the cosmological constant, the mysterious energy of empty space that is driving the accelerating expansion of the universe, an expansion that, it has not escaped some theorists' notice, is steadily increasing the volume of causally disconnected space, reducing the amount of the universe that needs to be simulated in real time. These connections might be coincidences. They might be examples of the human mind finding patterns where there are none. But they are also the kinds of connections that a genuinely rigorous simulation theory would need to make, the connections between the architecture of a computation and the physics it produces. And some of them are uncomfortably suggestive. Let us come, then, to the deepest and strangest version of the nested simulation problem. Let us come to the possibility that has no clean resolution, no comfortable resting place, no final answer that the mind can hold without feeling slightly dizzy. What if there is no base reality? What if the stack of simulations has no bottom? What if every reality is embedded in a larger one, every computation is running on a substrate that is itself a computation, in a regress that extends infinitely in the direction of the more fundamental? Not a stack with a foundation, but a stack with no foundation at all, turtles all the way down, forever, without end. This possibility is uncomfortable precisely because we cannot conceive of it. Our minds are built to understand objects by understanding what they're made of, to understand processes by understanding what runs them, to understand computations by understanding the hardware that executes them. A computation that is running on nothing, supported by nothing, embedded in nothing, a reality that simply is, at every level, computational all the way down, this is something our intuitions are not equipped to handle. It is a thought that slips, when you try to grip it, like water through a closed hand. And yet the alternative, the insistence on a base reality, a level that is simply and fundamentally real in a way that requires no further substrate, is not obviously more satisfying. What would it mean for something to be fundamentally, irreducibly real? What would the physics of the base layer look like? How would it be different from the physics of every other layer? The demand for a base reality might itself be a cognitive artifact, an assumption we bring to the problem without examining it, the residue of a childhood in which objects were solid and rooms had flaws. Perhaps reality, at whatever depth one investigates it, is simply formal structure all the way down. Perhaps existence is, at its core, computation without substrate, mathematics without material, information organized in precise and beautiful patterns that support whatever is built within them. Max Tegmark's mathematical universe hypothesis, which we explored when we discussed the Planck scale, sits at the far end of this road. If mathematics is not merely the language in which reality is described but the substance of which reality is made, then perhaps the question of what reality is running on is simply malformed. Perhaps it is running on nothing, in the sense that it is nothing but the patterns themselves, and the patterns are sufficient, the patterns are complete, the patterns are all there ever was or needed to be. This is either the most unsatisfying answer imaginable or the most beautiful one, depending on your temperament. It resolves the turtles all the way down regress by dissolving the question of the turtles entirely. There are no turtles. There is only the pattern of turtles. There is only the formal structure of a universe that describes itself being turtles, and the question of what the turtles stand on simply does not arise, because the turtles were never standing on anything, because standing is a feature of the pattern, not a feature of some underlying physical ground. We have traveled a long way tonight, you and I. We began in the cold open with the feeling that something is slightly off, that the regularity of physical law is a little too regular, that the mathematical nature of reality is a little too mathematical. We went down to the Planck scale and found something that might be a pixel. We followed the thread of simulation detection through the data of ultra-high-energy cosmic rays and the anomalies of the cosmic microwave background. And now we have arrived here, in the nested depths of the turtles all the way down problem, in the space where every substrate has a substrate and the regress of foundations may have no end. It is a dizzying place. And it is also, strangely, a peaceful one. Because notice what has not been lost in all of this depth. Notice what has persisted through every level of the stack, through every layer of simulation, through every stage of the descent. The experience of wondering is still here. The experience of following an idea carefully, of feeling the texture of a difficult thought, of arriving at a threshold and pausing before it with open curiosity, all of that is still present, still vivid, still real in whatever sense real can mean in this context. The physics of your neurons, the chemistry of your attention, the mathematics of your mind processing these words, whatever substrate supports them, however many levels down in the stack you are, however far the turtles extend below you, the experience itself is here, and it is entire. That is not a small thing. That is, in many ways, the most important thing. And it is where we will go next, into the question of what it means for an experience to be real when the substrate that generates it might itself be a computation. Into the hard and beautiful problem of consciousness inside the machine. But that is the territory that waits just ahead. For now, let this settle. Let the enormity of the nested problem rest lightly in the mind, like a stone in still water, finding its depth without disturbance. The universe is deeper than we can see. The stack of realities may be longer than we can count. And somewhere in the depths of it, whether there is a base or not, whether there is a bottom turtle or turtles forever, the fact of awareness persists. The fact of this moment, this breath, this quiet attention you are bringing to these enormous questions, persists. Hold that. Take it with you as we continue. Because we are going to need it. The remaining sections to cover are, Section 4, is the mind inside the machine real? Section 5, the exit, messages, escapes, and the simulators, and the closing meditation, sitting with unreality. There is a question that has waited patiently beneath everything we have explored tonight. It has waited beneath the Planck length and the lattice simulations and the nested towers of recursive reality. It is not a question about physics, exactly, though physics touches it at the edges. It is not a question about mathematics, though mathematics cannot fully escape it. It is the question that makes everything else feel suddenly, intimately urgent. And that question is simply this. Are you real? Not the atoms that compose the body resting wherever you are resting right now. Not the neurons firing their slow electrical murmurs through the soft geography of the brain. Those things we have already placed into question, already held up to the strange light of simulation theory and found them trembling slightly, uncertain of their own solidity. No. The question is about something else entirely. The question is about the feeling of being here. The sense of warmth, or the weight of the blanket, or the particular quality of the darkness behind your closed eyelids. The quiet hum of your own attention as it moves through these words and finds some of them interesting, and lets others drift by like leaves on a slow river. That feeling. That presence. Is it real? This is what philosophers call the hard problem of consciousness. And it is called hard not because it is complicated, the way quantum mechanics is complicated, not because the mathematics resists solution or the experiments are difficult to design. It is called hard because no one has the faintest idea where to even begin. The easy problems of consciousness, and they are only easy by comparison, involve explaining how the brain processes information, how it integrates sensory data, how it directs attention and generates behavior. These are genuinely difficult scientific questions, but they are the kind of difficult that science knows how to approach. You study the neurons. You map the networks. You trace the signals. Given enough time and ingenuity, you converge on answers. But the hard problem asks something different. It asks why any of that processing gives rise to experience at all. Why, when electrochemical signals cascade through the visual cortex, is there also the redness of red? Why, when pressure receptors in the fingertips fire, is there also the feeling of softness? Why is there something it is like to be you, rather than nothing? Why is there an inside? No physical or computational description has ever touched that question. We can describe the brain in extraordinary detail, map every synapse, model every ion channel, simulate the entire cascade of neural events that occurs when you hear a piece of music that moves you to tears, and at the end of the description we still have not explained the tears, not the salt water, but the ache. We have explained the mechanism and left the experience completely untouched, hovering above the physical account like a ghost that refuses to be reduced. Now hold that against the backdrop of everything we have been exploring. If reality is a simulation, then the neurons in your brain are simulated neurons. The electrochemical signals are simulated signals, patterns in a computation, mathematical relationships dancing through the lattice of some vast processing architecture that may or may not resemble anything we would recognize as a computer. And the question becomes even more vertiginous, even more strange, even more quietly astonishing. Can simulated neurons firing simulated signals generate real experience? There is a philosophical thought experiment that sharpens this question almost unbearably. It was introduced by the philosopher David Chalmers, and it involves what he calls a philosophical zombie. A philosophical zombie is not the lumbering, hungry creature of horror films. It is something far stranger and in some ways far more unsettling. A philosophical zombie is a being that is, in every physical and behavioral respect, identical to a conscious human being. It responds to pain by flinching. It reports feeling happy when good things happen. It says, when asked, that it is experiencing the color blue, that it finds music beautiful, that it remembers its childhood with a particular soft nostalgia. Every neuron fires exactly as it fires in a conscious brain. Every behavior, every response, every word, every gesture, identical. And yet, there is nothing it is like to be this zombie. There is no inner experience. The lights are on in every external sense, every measurable sense, every sense that could ever be captured by a scientific instrument or a behavioral test. But inside, nothing. No one home. The experience is absent, and its absence leaves no trace on anything that could be measured from the outside. The disturbing question that the philosophical zombie raises is not whether such beings could exist. The disturbing question is whether they could exist in principle, whether consciousness is the kind of thing that could, even theoretically, be absent from a system that is physically and functionally identical to a conscious one. And if the answer is yes, if such a zombie is even conceivable, then consciousness is not simply what the brain does. It is something over and above the physical process, something that the physical description leaves out, something extra, something irreducible. Now consider your fellow human beings. Consider the person sleeping beside you, or down the hall, or across the city in their own quiet darkness. You cannot access their inner experience. You can only observe their behavior, hear their words, watch their face. You assume, with a deep and nearly unexamined confidence, that there is something it is like to be them. That when they tell you they are sad, there is a sadness, an actual felt quality of sadness, occurring behind the words. But you cannot verify this. You have never been inside anyone else's experience. You take it on faith, on a very reasonable, very well-supported faith, but faith nonetheless. Now scale that uncertainty to its logical conclusion within a simulation. If the beings around you are computational constructs, if their neurons are simulated and their signals are mathematical, if their entire physical implementation is a process running on some vast and incomprehensible architecture of processing, does the uncertainty change? Is there any reason to believe that the simulated being is conscious where the philosophical zombie is not? Or any reason to believe it is not? There is a philosophical position that tries to cut through this knot with elegant efficiency. It is called functionalism, and its central claim is both simple and radical. Functionalism says that consciousness is not about what a system is made of. It is about what the system does. It is about the functional relationships, the patterns of information processing, the way inputs are transformed into outputs and integrated into a coherent whole. If two systems have the same functional organization, they have the same mental states, regardless of whether one is built from carbon-based neurons suspended in biological fluid and the other is built from silicon, all light, or the abstract mathematical relations of a simulated lattice. On this view, the substrate does not matter. The implementation does not matter. What matters is the pattern. And if the pattern is rich enough, integrated enough, complex enough, consciousness arises. Not as a byproduct, not as an afterthought, but as what that pattern is, from the inside. This is a deeply hopeful position for beings living inside a simulation. It says that even if the neurons are not made of real matter, even if the signals are not real electrochemistry, even if the entire physical theater of the brain is a kind of elaborate mathematical shadow play, the experience can still be genuine. The pattern is still there. The integration is still there. The inside is still there. But substrate dependence pushes back. Substrate dependence says that there is something special about the particular physical implementation of consciousness, that biological neurons, with their specific chemistry and their specific dynamics, generate experience in a way that an abstract functional equivalent simply does not. That there is something about the wetness, the continuity, the embodied biological reality of the brain that is not preserved in a purely mathematical or computational description. That a perfect simulation of water does not make anything wet. Neither view has won. Neither view may be provable, at least not with the tools we currently possess. And perhaps that is the right place to sit with this question, not in resolution, but in genuine, open uncertainty. Because the uncertainty itself is informative. It tells us that consciousness is not the kind of thing we yet understand well enough to make confident claims about. It tells us that the hard problem is genuinely hard. And it suggests, quietly, that any theory of reality, simulated or otherwise, that does not grapple with the fact of experience is leaving out the most important thing. Here is what cannot be taken from you, regardless of which position is correct. The experience of this moment. Whatever its ultimate metaphysical status, whatever the substrate on which it runs, whatever the nature of the computation or the biology or the divine machinery that generates it, the experience is occurring. You are having it. There is something it is like to be you, right now, in this particular quietness, with these particular thoughts moving through you like slow light through water. If the simulation hypothesis is true, and your consciousness is a pattern running on a vast computational substrate, then that pattern is real. The experience is real. The feeling of warmth is a real feeling. The softness of sleepiness gathering at the edges of awareness is genuinely soft. The fact that it is generated by mathematics rather than by conventional physics does not make it less present. Does not make it less yours. And if the simulation hypothesis is false, and you are a biological creature in a physical universe that is not someone else's computation, then the same is true. The experience is real. The feeling is yours. The moment is genuine. In this way, consciousness may be the one thing that remains invariant across all possible theories of reality. The one fixed point that does not move when everything else dissolves into uncertainty. Whatever the universe is, however deep the stack of simulations runs, however the physics resolves at its most fundamental level, there is this. The quiet fact of being here. And that fact is not small. Let it settle. Let it be enough. For a moment, just let it be enough to be here, feeling whatever you are feeling, held in the gentle gravity of these enormous questions without needing to answer them. And now we come to the last question. The one that lives at the edge of everything we have explored. The one that feels most like science fiction and yet is, in its own strange way, the most scientifically tractable of all the questions we have asked tonight. If we are inside a simulation, is there a door? Think, for a moment, about what it would mean to be a character inside a video game who becomes aware. Not in the science fiction sense of dramatic awakening, but in the quiet, philosophical sense of the kind we have been exploring tonight. A character who begins to notice the seams. Who begins to suspect that the world they inhabit has edges, that the physics they experience is rendered rather than intrinsic, that somewhere beyond the horizon of their perception there is a different kind of reality, a room, a screen, a hand on a controller, a being of a fundamentally different nature watching. What could that character do? They could study the physics of their world with extraordinary precision, as we have done. They could look for the pixel at the bottom of things, for the cutoff in the cosmic ray spectrum, for the anomalies in the pattern of the sky. They could construct arguments, as Bostrom did, about the statistical likelihood of their situation. They could develop theories, write papers, make podcasts, lie in the quiet dark and wonder. And all of that would be remarkable. All of that would represent a kind of consciousness pressing against the walls of its own container, trying to feel the shape of the box from the inside. But could they reach through? There are theoretical mechanisms, speculative but not entirely without foundation, through which a civilization advanced enough might attempt to signal beyond the boundaries of a simulated reality. Consider the nature of computational limits. Every simulation, regardless of how powerful the hardware that runs it, has finite resources. There are constraints on processing speed, on memory, on the precision with which states can be represented. And those constraints, as we explored in the context of Silas Bean's work, may leave signatures in the physics of the simulated world, energy cutoffs, resolution limits, the discrete lattice structure of space itself. But they may also leave exploits. In any computational system, there are edge cases. There are situations that the designers did not fully anticipate, inputs that produce unexpected outputs, corners of the parameter space where the system behaves in ways that were not intended. We call these bugs, or we call them glitches, or in more extreme cases we call them exploits, vulnerabilities that a sufficiently clever agent can use to do things the system was not designed to allow. Anyone who has played video games with any depth of engagement has encountered this, the wall that can be walked through if you approach it at exactly the right angle, the sequence of actions that produces an impossible item, the corner of the map where the geometry breaks down and you fall through the floor into a gray void. If our reality is a simulation, it may have exploits. It may have regions of the parameter space, corners of the physics, edge cases in the mathematics, where the rules break down in ways that reveal the underlying structure. And a sufficiently advanced civilization, one that had mapped the physics of their world to a precision far beyond what we have currently achieved, that had tested every edge, pushed every boundary, that had, in essence, speed-ran the simulation in search of out-of-bounds geometry, might find one. What they would find on the other side is entirely beyond speculation. Whether there is a room with a screen, a vast computational architecture that bears no resemblance to anything we would recognize, an entity that experiences reality in dimensions we have no framework for perceiving, these are questions that collapse language and take imagination beyond its comfortable limits. There is another approach, perhaps quieter and more elegant, that does not require finding an exploit but rather finding a message. If our simulators are not merely observers, if they are, in some sense, interested in what happens inside their simulation, curious about whether the beings within it develop the capacity for self-reflection, for philosophy, for science, for the particular strange recursive act of wondering whether they are simulated, then they might communicate. Not necessarily in any form we would recognize as communication. Not in a voice from the sky or a message written in the stars. But perhaps in the structure of the physics itself. Perhaps in the particular values of the fundamental constants, the fine structure constant, the ratio of the electromagnetic force to gravity, the precise mass of the electron, values that seem exquisitely, almost unnervingly fine-tuned to permit the existence of complexity, of chemistry, of life, of minds capable of asking this very question. Is that fine-tuning a message? Is it a signature, the equivalent of an artist's initials worked into the lower corner of a canvas? Or is it simply the anthropic principle, the observation that we could only find ourselves in a universe with constants compatible with our existence, because a universe with different constants would contain no one to notice? The answer, as with so much in this territory, remains genuinely, beautifully open. But consider this. If you were a simulator, and you had created a world rich enough to generate consciousness, rich enough to generate curiosity, rich enough to produce beings who would eventually, inevitably, begin to suspect the nature of their reality, would you not be watching for that moment? Would you not be waiting, with something that in your own incomprehensible way resembles anticipation, for the moment when the beings in the box looked up and asked the right question? And if they did, if we have, what would you do? There are several possibilities, and they are not mutually exclusive. The first is silence. Perhaps the simulators have reasons, scientific or ethical or simply procedural, for maintaining what we might think of as experimental integrity. Perhaps the simulation exists precisely to observe what happens when consciousness develops without external intervention, and the protocol demands non-interference. In this case, we would never receive a signal, never find a message, never encounter a boundary that we could cross. We would press against the walls of the box forever, unable to feel them, unable to verify or refute our suspicions, left only with the mathematics and the philosophy and the long quiet wondering. The second possibility is intervention, subtle, ongoing, barely perceptible. Perhaps the simulators do communicate, but in ways woven so deeply into the fabric of the simulation that we interpret them as physics rather than messages, as natural law rather than instructions. Perhaps the sense that the universe is mathematical, that it seems almost designed to be legible to minds capable of mathematics, is not a coincidence. Perhaps it is a door, left slightly ajar, and the mathematics is the crack of light beneath it. The third possibility is the most disorienting, and perhaps the most wonderful. Perhaps the simulators have already reached through. Perhaps there are moments in which the boundary between simulation and base reality becomes, in some controlled and limited way, permeable. Perhaps what we experience as moments of profound insight, of sudden clarity, of the particular variety of all that comes when you grasp something true about the structure of the universe and feel, briefly, that you are touching something real and solid beneath the surface of things. Perhaps those moments are contact. This is speculation. It is beautiful speculation, and it is worth sitting with, but it makes no testable predictions and carries no scientific weight. What it carries instead is something else, a quality of openness, of permission to hold the mystery without forcing it into a shape. The shape of the mystery is its own shape, and forcing it to become an answer, any answer, loses something essential about what the mystery is. The characters in a video game who become aware cannot leave the screen. But they can, within the screen, do something extraordinary. They can choose to live as though the experience is real. They can love other characters whose experience is equally uncertain. They can build beautiful things within the limits of the simulation. They can be kind and curious and generous and brave. They can look up at the rendered sky and find it genuinely beautiful, not because they have verified its ultimate metaphysical status, but because beauty is not a property of the substrate. Beauty is a relationship between a perceiving mind and the thing perceived. And if the mind is real, if the experience is real, if the inside is genuinely lit, then the beauty is real, regardless of what is on the other side of the screen. This is, perhaps, the most important conclusion available to us. Not that we have solved the question of whether we are simulated. We have not. Not that we have found the exit, or contacted the simulators, or mapped the edges of the lattice. We have not done any of those things, though we have looked carefully at some intriguing hints and anomalies. The most important conclusion is that the question does not diminish the experience. That asking whether reality is simulated does not subtract from the reality of the feeling of asking. That the inquiry does not dissolve the inquirer. You are still here. The darkness is still soft. The weight of the night is still gentle. And the question, the vast, luminous, unanswered question of what this all is and why it is the way it is and whether there is someone watching from the other side, that question is itself a beautiful thing. A gift of consciousness to itself. The universe's way of becoming curious about its own nature, through the improbable instrument of you, lying here in the dark, breathing slowly, thinking enormous thoughts. And so we arrive, at last, at the place where narration gives way to silence. Where words have carried us as far as words can carry anyone, and what remains is not more information but something quieter and more fundamental. What remains is the experience itself. The fact of being here. The soft persistence of awareness in the dark. Everything we have explored tonight was an act of attention. Attention to the pixel at the bottom of reality. Attention to the seams in the code of space-time. Attention to the vertiginous depth of nested simulations, each containing the last like mirrors facing mirrors into an infinite interior. Attention to the extraordinary, irreducible fact of consciousness, the light that is somehow lit inside the machine, whether the machine is biological or mathematical or something we have no name for yet. And attention to the exit question, the door that may or may not exist, the simulators who may or may not be watching, the mystery that deepens the more carefully you look. All of that attention was real. Whatever its substrate, whatever its ultimate physical or computational nature, the attention was genuine. It moved through the material of these ideas and found some of them beautiful and some of them unsettling and perhaps some of them strangely, unexpectedly comforting. Because there is comfort here, if you let yourself find it. The comfort of being in the company of uncertainty without being destroyed by it. The comfort of being a mind large enough to hold a question it cannot answer. The comfort of knowing that consciousness, yours, specifically yours, is the most extraordinary thing we have encountered in all of this exploration, more mysterious than the Planck length, more improbable than the fine-tuned constants, more irreducible than the hard problem. More stubborn than any simulation. Now let the questions rest. They will be there when you return to them. They are patient. They have waited at the edge of human awareness for as long as there have been humans aware enough to reach them, and they will wait a little longer while you sleep. Feel the weight of the body settling. Feel the way the breath has slowed, almost without you noticing, over the course of this long, quiet exploration. The inhale comes gently, and releases, and the space between breaths is peaceful. The space between thoughts is growing wider, like the space between stars when you pull back far enough to see the true scale of things. Let the Planck length dissolve into abstraction. Let the lattice of simulated space-time become something distant and soft, like the sound of wind through leaves at the edge of sleep. Let the nested simulations fold into one another until they become simply depth. A sense of depth beneath things, beneath everything, an infinite interior that does not require you to map it. It is enough to know it is there. It is enough to rest at the surface of it, the way a leaf rests on the surface of very deep water, held up by something it cannot see. Let the philosophical zombies and the hard problem of consciousness and the question of what is real inside the machine, let those dissolve too. Not because they are not important, they are profoundly important, and you will return to them. But because the most direct answer to the hard problem of consciousness is this: you are having an experience right now. Not a simulated approximation of an experience. An experience. The inside is lit. The feeling is here. And no philosophical argument has yet managed to take that away from anyone, because the person being argued at is already the evidence. You are already the proof. Rest in that. Let it be a kind of anchor as everything else drifts loose into the soft dark of sleep. The experience is real. The inside is lit. You are here. The breath comes and goes, and the thoughts grow slow and strange, the way they do at the edge of dreaming, taking on shapes that feel significant without quite resolving into meaning. That is all right. That is exactly right. The edge of dreaming is its own kind of threshold, its own kind of doorway between one mode of awareness and another. And you are moving toward it now, slowly, without effort, the way a boat moves with a current it can barely feel. The universe outside, however deep it stack, however many simulations nest within simulations within simulations, however the physics resolves at the very bottom of things, the universe outside is quiet tonight. The cosmic rays are tracing their invisible paths through the dark. The lattice of spacetime, if it is a lattice, is holding steady at its Planck scale resolution, faithful and fine, the way a dream holds its own logic until the moment you wake. The CMB is still singing its ancient, nearly inaudible song, the echo of whatever beginning began all of this. And you are here. Aware. Breathing. Held. The questions we asked tonight do not have answers yet. They may not have answers in your lifetime, or in any lifetime of anyone alive on this improbable planet. But they are good questions. The best kind of questions, the kind that open outward rather than closing down, that make the world larger rather than smaller, that leave you standing at the edge of something vast and finding the vastness beautiful rather than terrible. The simulation or not, this consciousness persists. This moment persists. The caring you bring to things, the love you carry, the particular texture of your attention and your humor and your grief and your wonder, that is not diminished by uncertainty about the substrate. It is not made less real by the possibility that reality is deeper than it appears. It is, if anything, made more extraordinary. Because whatever the physics, whatever the architecture, whatever is running on whatever, this emerged. You emerged. The capacity for wonder emerged. The capacity to lie in the dark and ask enormous questions about the nature of reality emerged. That is astonishing. That is, on any account, genuinely astonishing. Sleep now. Let the astonishment settle into quiet. Let the enormous questions fold themselves up like maps, carefully, to be opened again in another light, at another time, when you are rested and ready and curious again. They will keep. They have kept for millennia. They will keep for you tonight. The breath is slow and warm, and the darkness is the right kind of dark, the restful kind, the kind that holds rather than presses. Next time, we will go somewhere new. We will follow a different thread from the same great mystery, closer, perhaps, to the question of what the simulators might be, what intelligence at the level of a civilization capable of creating realities might look like, what it might want, what it might feel. We will go, gently and carefully and with the same slow attention we brought here tonight, into the question of the mind behind the machine. But that is next time. Tonight is for rest. The universe holds you. Whatever the universe is, matter, mathematics, computation, mystery, it holds you. You are inside it, and it is inside you, and the boundary between them has always been more permeable than it appears. The breath moves both ways. The awareness reaches out and the world reaches in, and somewhere in that quiet exchange, something called experience is always occurring. It is occurring now. It is soft. It is yours. Sleep well.